Chapter 1, Exercise 16, ABC. Interpret the problem as a geometric one, where we want to determine the intersection of two spheres of equal radii and given centers. Here is a picture. Assume 2r greater than d. That means that r greater than d over 2 equals absolute value x minus y over 2. Then, intuitively, we know that the intersection between the spheres SXR and SYR is not empty. But we want to know that such an intersection contains an infinite number of points. Here, we have this. Denotes a sphere with center V and radius R. Claim: if W satisfies dot product of W and x minus y equals 0, and absolute value W squared equals R squared minus D squared over 4, then Z equals half x plus half y plus W satisfies absolute value Z minus x equals absolute value Z minus y equals R. Absolute value Z minus x squared ultimately equals R squared. A similar relation holds for Z minus y absolute valued squared. From linear algebra, it is known that there are infinitely many distinct solutions W for both equations. Dot product W x minus y equals 0, and absolute value W squared equals R squared minus D squared over 4. Consequently, there are infinitely many Z such that absolute value Z minus x equals absolute value Z minus y equals R. From a geometric viewpoint, such W are on a hyperplane π, which is perpendicular to the vector x minus y, and passes through its midpoint, half x plus half y. Hence, the points Z are on π, but more specifically, they are on the hypersphere with center half x plus half y and radius R squared minus D squared over 4. If 2r equals d, then intuitively, the intersection between the spheres SXR and SYR is one point, the midpoint, half x plus half y. Using the same argument as before, we have absolute value W squared equals 0 and Z equals half x plus half y. Assume 2r less than d. If Z were to satisfy this condition, the triangle inequality would be violated. That is, we would have absolute value x minus y equals d greater than 2r equals absolute value x minus z plus absolute value z minus y. Thus, the intersection is empty. When k equals 2, there are thus two solutions for case A. Cases B and C do not require modifications. Using the Pythagorean theorem, we have the coordinates of the intersection points being this. Above, M is the midpoint between x and y, and R is the radius. The problem for k equals 3 is a generalization of this result. That is, if we rotate these points with respect to the line xy, then we obtain a circle. The same idea applies for the other two cases. When k equals 1, there are no solutions for case A. Cases B and C do not require modifications. In this case, the quote-unquote spheres are only 2-point sets, and this is the reason why there are no solutions for case A. Also, none for C. However, for B, we have R equals D over 2, and so one point is common. Thanks for watching.